So here we go. My name is Kirill. I will hopefully show you my presentation on low-code edge intelligence in smart factories. There is always a good and a bad thing talking after David, because I actually will repeat and recap the points that he mentioned in his motivation. Our motivation is more or less the same. Good that your talk didn't go on television, my will.
We say that you should go first and let you go second.
Yeah, but then you will have the problem. The motivation for more flexible manufacturing than it is done today. Again, I will repeat what David said. We require more flexible productions. We require to produce the goods in small series, in the small batches, because the demand is for more individualized products. Let me just mute this. These individualized products require the reconfigurable manufacturing, because if you get the orders in the small batches every time, you would need to reconfigure a factory and for the order that is coming up. This makes our factories more complex, and in order to deal with this complexity, we would need to also somehow manage the software that is controlling these stations, these manufacturing processes. So in SmartEdge, we are looking at the edge intelligence and low-code applications for control software using the concepts of the recipes, and also how do we develop the recipes how do we define the capabilities, how do we define the skills, how do we define the workflows and all of that. And if the order's changing frequently, how we reconfigure the software as well. The benefits that we are looking to are the quick adaptation, both of the hardwares and softwares, that allows to do this individualized production, and it will be more sustainable, more ecological, just like David described in his slides. The thing is that if we look at the state of the art, and if you come with any of those ideas to the factory, you will hear this one, because on the shop floors there are normally the systems running since 1980s, 70s, in contrast to the automotive use case that Kari described, so in the city of Helsinki there are politicians that are not happy about if something goes wrong. So there might be the implications for them who allow these guys to come to the streets. In the factories, every seconds, minutes, or even hours that the production line is standing still, it's dollars, euros, whatever. And these are the numbers that goes like out of the roof pretty fast. So you cannot test these things in a real environment. You need to build something and you need to prove it really for the 100%, so that people are sure that what you offer them is of any advantage and that it works. So this is our playground. This is our laboratory at Siemens, where we really do the things that I've just described. So it's a manufacturing line. So you see in the background there is this hexagon shape, which is pretty much the classical conveyor that you would see in any factory nowadays as well. There are also the standalone manufacturing cells. So every cell that you see, every robotic cell does a job. This is how David described this as flexible robotic manufacturing cells. Every of these cells is there for some particular task. So I will describe it on the next slide for the hexagon part, but you get the idea that each of those does one production step that it is responsible for. And we have those standalone robotic cells also to show the flexibility of the transport system. So we use the AGVs, the classical ones, that are taught to follow specific passes between the stations, but still it's a flexibility to bring the products or product parts between one station and another. And you are all welcome to follow the URL or QR code to take like a virtual excursion to our laboratory. There is a description of all the stations and more. So there is lots of material about our lab. And everything that you see virtually, we have like physically installed in Nuremberg, and this is the playground that we'll use in the project. So a bit about the process. I will not describe all the parts, but like the main steps that are required. On the left top side, you see the product that we are building. It's from another manufacturing line, but it's very similar to what we are building in Nuremberg. You have 5 different types of shapes that you put on the plate, and this is the flexibility of the order that you have. So you can choose whatever type of shapes you want to put on this pallet. What's the order of that shapes? You can put the 5 of yellow ones. You can put red, blue, green, yellow, whatever you choose, and then the order goes to the manufacturing line, and first it goes to the assembly working machine that has a storage of different parts, and then it assembles the product and puts it to the pallet, to this plate. Then assembly station, when it's done with the getting your order done, then it unloads the pallet with all the shapes to the hexagon conveyor belt, and then the pallet moves to the next station, which is quality inspection station, which also takes it from the hexagon, puts it to the robot. Robot brings the pallet in front of the camera, and then there is some inspection done that, for example, the order is assembled according to your needs, as it was ordered, or something else if there are any scratches in the part. So this is the working station where we want to run some AI learning processes and do this quality inspection with AI on the edge. After the quality inspection is done, again, the robot unloads it to the hexagon conveyor belt. It goes to the what they call recycling module or disassemble module. So at the end, last robot picks it from the hexagon conveyor belt and disassembles the product, so puts different shapes into different storages, and then you can refill the assemble station in the beginning so that you can continuously run the same process. So there are also the standalone working station where the AGVs can bring the products if there are any needs for additional working steps, but I will spare some time. So how does this work? The fundamental communication protocol that we use in our laboratory and also an established industrial protocol is OPC-UA. And with OPC-UA, you always have 2 sides. You have communication protocol and you have the information modeling part. So as a communication protocol, OPC-UA started in 2006. And it's platform independent, so it works across various operating systems, in contrast to its classical OPC version, which only worked on Windows. So OPC-UA is platform independent. It has security mechanisms, so that allows you the secure communication. It's interoperable between different devices, different vendors, scalable up to the cloud. With its pub-sub mechanism, it's even real-time, hard real-time, so in terms of industry, you can get the real-time communication with OPC-UA, and also you can combine OPC-UA with other existing industrial protocols and also with IoT protocols such as MQTT and AMQP. The other part of the story is that OPC-UA is a tool for information modeling. So OPC-UA offers you a way how to model your objects. So it becomes like object-oriented model. that you use, and on top you can use your own modeling. So you can create your processes, you can create your data models in OPC UA. This is the part where we will do the skills and capabilities modeling. So this will be our answer to this ontology part. We will do it in OPC UA. We need to see how we do more or less the same with Web of Things, but I will speak about it tomorrow more. Yeah, you get the standardized information models from the community. These are the things like robotics companion specification. So there is an agreement how we describe a robot using the OPC UA information model. And if different robotics vendors use this companion specification, then it's the same for KUKA robot and for universal robots. So you can access the data from a robot in a similar way. So this is the whole layered architecture of OPC UA. On the bottom you have your own protocol. So as I said, it can be mapped any industrial protocol to OPC UA. This is kind of a glue code. Then on top you have either client-server architecture or pub/sub, which gives you access to the data which is described according to information model of the OPC UA. So it gives you the objects with its methods, with its attributes, kind of like in object-oriented programming. And on top of that foundational model, you have core information models. So this gives you alarms, events, state machines. How do you describe the state machines in OPC UA? On top, you have the companion specifications. So this is something where domain-specific models are in. And on very top, you can create your own information model for example, for your plant, that all the devices that you use in your plant are modeled in the same way. Okay. The drawback of these cool ideas and these cool things is the complexity, the difficulty of the models that we get there. This is an example from robotics companion specification, and the robotics companion specification itself depends on two other models in OPC UA. So in order to use it, you need to understand at least 3 other models, or 3 models including robotics companion specification, and all of those are a huge, so every specification is a huge document of more than 100 pages. So in order to understand it, you really need to study a lot. Here I wanted to give you an example of this actual position of a robot. So this is the way how the robotic companion specification envisions how any robot, be it KUKA robot, be it universal robots, or any other robot that uses OPC UA companion specification, defines the axis of that robot and how to find its actual position. You would need to know that there is a component type and an axis type that is a component type, and this axis type has a parameter set, an attribute, and this attribute has a couple of other attributes. Among others, there is an actual position. Here, if I can quickly switch, I will show you. So this is an, oh, you don't see it, sorry, I need to bring it up here. Here you see an OPC UA client that I'm using that connects to an OPC UA server that controls different robots that are modeled according to the robotics companion specification of OPC UA. And I am looking for my Siemens robot that controls one of the workstations in our autonomous factory lab, and I want to find out where its actual position parameter is. So here I already did all the clicks, and you see that under the object robot, which I could see from the beginning because it's in the root, I would need to know that there is motion devices folder. In motion devices folder, there is actually this is an array of an object that specify all the motion devices that are controlled by this robot. There is a folder axis. In the axis, there are 3 axes of this robot, and there is a parameter set, and in order to find the position of this robot, I would need to go for actual position. So this is cumbersome. Even if I know where to look at, it's cumbersome to find the node that I'm looking for. And actually, this is the only way how you can communicate with the robots that is modeled with the companion spec. So you always look for the information that is hidden underneath, under all this modeling stuff. Let's proceed. Yep. But OPCUA is a cool thing. This is what actually lots of people in the industry using. Every Siemens POC is nowadays coming with OPCUA server integrated, so it's there. So why don't use it to define the capabilities and skills, as it has this modeling capabilities integrated, so we can on top put our own SmartEdge model and define the capabilities and the skills of different devices. And capabilities and skills are there to make another level of abstraction from the PLC code, from really running implementation of a skill, and to offer unified way to access the capabilities of the devices. And when we say capability, we think about something implementation independent, abstract thing, something like transport or pick and place. So it doesn't really look into how you implement pick and place process. Who is doing that? Is it a robot? Is it, I don't know, a human that does pick and place, or any other device? There is a capability, or even you can do transport with pick and place, something like that. So this is all that we envision to model in capabilities. And skill has its skill implementation, which is a running POC code in our case, or any program actually that executes a skill. And there is skill interface. So the skill interface is the way how do you access this, how do you execute it, and this is something that we want to have a unified over all our devices. So that the skill interface is more or less the same for every process that we have. So yeah, for capabilities, this will be would be an ontology, something like David already mentioned, ontology of all the capabilities that can be around for this specific use case. For skill interface, we are using OPCUA and also want to use Web of Things in the project. Skill implementation will be use case specific, so any running code can be here. And here we go to the simplified demonstrator architecture. So as I showed you, there are more than 4 working stations that I have here on the slide, but the principle is the same. So we have the POCs that are controlling the stations. All the POCs have the OPCUA information model and the OPCUA interface to access the data and to execute its functionality. And on top, what you see in the middle, WinCC is a SCADA system, so this would be a classical solution how the POCs are controlled nowadays. And we want to use Mendix, which provides us with the low-code functionalities so that we can achieve this level of flexibility of rearranging our software blocks and to make this recipe-based software engineering. So quickly introduce you to Mendix. This is a product, a low-code development platform from Siemens, which does actually low-code. And there are existing building blocks in Mendix. So there are function blocks that you can use from the beginning. And you also can create the function blocks for your own needs. And this is the way where we want to use the skills. So we see the skills of the workstations in our plant as the function blocks in Mendix. And then based on the capabilities matching, we want to define the recipes, which will be implementation independent, saying that I want to transport this from A to B. And then based on the skills of manufacturing cells, so of the devices down there on the shop floor, we want to match the recipe which says transport with existing skills of a hexagon conveyor belt, for example, that tells that it can bring our product from station A to station B. Yeah, so there are lots of features that I would skip for now. There is an IDE that is free, so you can all download it, test Mendix, and try it for your needs. There is some little limitation, which is about running the Mendix runtime. So if you use the free version, Mendix runtime stops your application every 2 to 4 hours. But for testing purposes, it's enough. And all the rest, so all the functionality is there in the free version. So this is actually what I'm using, and totally enough for research and development activities. It's composed of domain models. So in Mendix itself, internally, you can define the domain models. This is also the place where we see the capabilities and skills. It defines the logic. I will show you a couple of examples later. Logic is what we see as a recipe. It's a workflow. If you know, it uses BPMN, so this is kind of sequence of activities that need to be run in order to execute a recipe. And yeah, you get also the web pages more or less semi-automatically generated for you that you use for your web application to interact with Mendix. And here come the recipes. So the recipes in SmartEdge as we see them is a sequence of steps, a sequence of capabilities that need to be executed in order to run manufacturing process. So every N node that you see here would be a skill invocation. Every C node in between would be some business logic, what I do with the output of one skill and how do I pass the data to the next one, to the next production step. We have a way, so we envision how we can serialize these Mendix workflows in order to store them in RDF graph to also match make the existing recipes, what capabilities they use, yeah, and what is the workflow for this specific recipe. This should work as follows. So any Mendix recipe can be serialized in binary JSON data. And on top of this binary JSON data, you can create, so out of this binary JSON data, you can create a recipe representation in a knowledge graph. So this is a running recipe. If you imagine that there are a couple of devices that I want to put together to execute some production process. For example, 2 devices speak Web of Things. It has they have a thing description for their skills, and OPCUA for the third device has a node set as a robot that I showed you before, which has a set of skills for the robot movement. We want to store both thing descriptions and OPCUA node information models in a knowledge graph. In order to have the skills they offer in a knowledge graph. And based on the skills of the existing devices and the recipes that define the capabilities that are needed for execution of this specific recipe, we do a matchmaking that device 1 can execute the action N1 for you, device 2 can do N2, device 3 can do N3. And then with the connectors, we execute the overall process. Here is an example of a recipe back to our use case. We first configure a product. This is what I described you, where you say which types of the blocks you want to see on your palette, in what order. We also check if there are available blocks in the storage. So it's always the case that you must check that if you ordered 5 blue blocks, that there are 5 blue blocks available in the assembly module. And if it's the case, we call the skill, which is manufacture a product, which will be then split into the separate skills, bring the pallet to the assembly station, assemble the product, bring it further, and so on, and execute the process that I have described. This is the implementation architecture, how it looks like. We have the POCs controlling the workstations. On top, we have the OPC UA. On top of OPC UA communication, we have the OPC UA information model. On top, we use robotics companion specification to model the robots according to the standard that is there. And all this goes to the Mendix recipe model, where we define the recipe. And then whenever we run Mendix runtime uses OPC UA connector to get back to the POCs and to get the data. Now we are slowly coming to the highlight, which will be a demo that I will try to run. What we have now is that assembly module on the right-hand side. This is a real machine that is standing in Nuremberg. We also have a metaverse digital twin of this one, which uses the same OPC UA server as the assembly module, the real one. So we have a digital twin that has the same interface and the same information model as the real machine. We put the model of the OPC UA server, so here there are 2 arrows. In reality, there is only one, so we put the node set of this OPC UA server, the model of the data, into the knowledge graph so that we can see which nodes are there, so which skills are there at the end of the day. And the thing that we are researching now extensively is if we can use large language models in order to search this graph. So LLM is there basically in order to user to define their queries, to define their queries to the knowledge graph in natural language to find the nodes that user can use for his/her recipes. So this should avoid the cumbersome process that I showed you. In order to find your actual position, you just ask the chat, and chat should give you kind of the address of this node or address of this skill as an answer. And now let's try to run the demo. So please bear with me. I might restart some things a couple of times because there are stable things running and there are also not very stable components here, but I will try to show you what we have here. May I just duplicate it for a while? So now you see what I see. That's good. So I have here 4 components. The one is the industrial metaverse model of the robot. It's pretty stupid. So for now, it only has this axis that you see on the right-hand side. You only see the horizontal part. And it can go from the right to the very left, and this is the only movement that is implemented right now, and go back. And this is what we will try to do now. There is an OPC UA server that controls the assembly station. I showed it to you already, so I can probably quickly show you, like in this way, how it works. So whenever a server gets a value of -1, it goes to the left. There is still some delay between the server and the industrial metaverse. The next part that I wanted to show you is, this is the LLM backend, and this is here to get the natural language requests from Mendix application and try to formulate a SPACO query that will find the node that I will be using in my recipe in order to control the current position of an axis. And the last but not least is the Mendix application that has these chat capabilities. This one is down as well. So Mendix has the interface to chat with the knowledge graph to get the data from there, and then if you find the node you want to control, it generates a read and write for you, so you can either read the current position of the robot and or put it to the new position. Let's just wait for Mendix to start up. Also takes some time from time to time. More than that, if you put Mendix into a Docker, then Docker will rerun it for you the runtime. So there is a workaround. So we are almost there. It says starting, and then when it says running, then we can try it again. Yep. So let's try it out again. So what we can query it for is something like, what is the node ID of current position of axis 1 of my robot? And this then goes to this guy. Yep. And it has already the TTL model, so it has already the graph there. What it tries to do is to come up with a SPACO query that will do exactly what I asked it for. This also takes some time, but let's see if we are successful here. In the answer window, we should get the node ID of the current position of the robot. Also, sometimes it works, sometimes it doesn't. So I have it already converted to TTL, and then every time I ask a question, I send it from Mendix to the back. For this one, it takes about, we got it now, about 15-20 seconds to get an answer from it.
Design time, so that
Yeah. We are always in the design time here. So this is it. This is the node ID. This is address that I was actually looking for. You see it here as well. So the namespace, whenever you have a running OPC UA server, it converts the URI to a namespace index. So 4 stands for Siemens COM OPC UA demo instance here, and the node ID is integer 6009. And the last thing that I wanted to demonstrate you is that I can here click on add write, and what this thing does, it also creates an OPC UA client in Mendix that tries to get to the server, connect to the server, and write a new value. Again, if we will be successful now, we should see that an axis goes from very right to very left. This is the same thing that I've done with an OPC UA client, but this time is from Mendix. So let's try to write -1 here and see if it works. At some point, yeah, now the server got it, and at the end the metaverse should get it too, and then it should go and move if it will be so kind. But this requires, now I lost the connection between the metaverse and OPC UA, I guess. So if I restart this one, when it starts up, it will go to the left. This will require also this knowledge of that -1 is left, 1 is right, somehow encoded into OPC UA as well. For now, it's just an integer, and the knowledge that -1 is left, 1 is right is in my head, actually. Yeah, now it works. Okay. So Mendix wrote it to OPCUA and to Metaverse.